Hi, everybody. It's Professor Mitchell. We're finishing up Chapter 6 today by looking at Section 6.6 on vectors. So if you've ever taken a physics class, a lot of this will probably be familiar to you. In this section, we're going to look at using magnitude and direction to show vectors are equal, visualize scalar multiplication, vector addition, and vector subtraction as geometric vectors, represent vectors in the rectangular coordinate system, perform operations with vectors in terms of I and j, find the unit vector in the direction of v, write a vector in terms of its magnitude and direction, and finally solve applied problems involving vectors. So a vector is a quantity that involves both a magnitude and a direction. This is called a vector quantity or just a vector. Quantities that involve magnitude but no direction are called scalar quantities or scalars. So just to give you a quick example, if I say that the wind is blowing 20 miles an hour, that would be a scalar because it doesn't have any direction attached to it. But when they say the wind is blowing 20 miles an hour from the southwest, you could represent that as a vector because it has magnitude, 20 miles per hour, and it also has direction. So a line segment to which a direction has been assigned is called a directed line segment. We call P the initial point and Q the terminal point. We denote this directed line segment like this, PQ with an arrow over it. The magnitude of the directed line segment, PQ, is its length. We denote this the way that you see here, PQ with the arrow over it, and then a pair of what look like double absolute value bars. Geometrically, a vector is a directed line segment. So you can see a picture of the vector PQ over here. So there are different ways of representing vectors depending on whether you're writing them on a piece of paper or reading them in a printed book. So when you're reading them in a printed book or say on a PowerPoint, typically a vector will be represented by a boldface lowercase letter. Now, because it's kind of hard to handwrite boldface, it's become traditional that when you write them on paper, you just write them as a letter, usually V or W, sometimes U, with an arrow over it. And then the magnitude, that works the same way, whether you're using print or handwriting. It's the double absolute value bars. Notice that it's the boldface V here, or the V with an arrow over it if it's handwritten. In general, vectors V and W are equal if they have the same magnitude and the same direction. And we will write this as V equals W. So here's a picture of two equal vectors in example A here, V equals W, because the vectors have the same magnitude and the same direction. In this example, the vectors have the same magnitude, they have the same length, but they have different directions. So these two vectors would not be equal. These two vectors almost look like they're equal, but they actually have opposite directions. So those two vectors are not equal. And finally, these two vectors have the same direction, but different magnitudes. So they would not be equal. So there are different ways to show that two vectors are equal. Equal vectors have the same magnitude and the same direction. So to show that they have the same magnitude, you can use the distance formula. So notice that the terminal and the initial and terminal points of both of these vectors are given. So using the distance formula that we talked about way back in chapter 1, the magnitude of vector u would be given by this formula. So replacing, let's see, x1, y1 with 2 negative, let's see, how did they do that? Now this is okay. They just, for some reason, they put x2 minus x1 squared over here. And they put y2 minus y1 squared over here. It doesn't matter, right? Just confused me there for a second. So that comes out to 5. And similarly, the magnitude of V, let's see, did they do the same thing this time? Yes, they did. They put y1 minus y2 squared over here, and they put x2 minus x1 squared over here. I wonder why they did that. Anyway, that also comes out to 5. All right, so these two vectors have the same magnitude. Now we just have to show they have the same direction. So one way to do that is to show that they have the same slope, but then you have to be careful because the slope is not going to differentiate between vectors that have exactly the opposite direction. All right, think about that for a second. Imagine that vector v was pointing in the opposite direction. When you find the slope of a line, lines don't have direction, right? So it wouldn't be able to tell the difference. So you do have to make sure, once you've shown that they have the same slope, that they are not opposites. So the slope of the first line that contains vector u is 4/3. And the slope of the line containing vector v is also 4/3. And since these two vectors both point up and to the right, they are not opposites, okay? If one of them pointed up and to the right and the other one pointed down and to the left, they could both have slope 4/3, but they would be opposites, okay? So at this point, I'm convinced that these two vectors have the same magnitude and the same direction, so those two vectors are equal. All right, scalar multiplication. The multiplication of a real number k and a vector v is called scalar multiplication, and we write this product like this. Notice that the k is not boldface, all right? There is actually a point in this PowerPoint where they used boldface where they weren't supposed to, and I'm going to be honest with you, I was just too lazy to change it. So I'm going to point it out to you when we get there. All right, but that's an easy mistake to make. So this is what scalar multiplication looks like. Here's vector v. Vector 2v would be the vector that has the same direction and is exactly twice as long. The vector 1/2 v would have the same direction and would be half as long. And then the vector -3/2 v would be 1.5 times as long as v and would point in the opposite direction. Okay, so that's how that works. All right, and in general, multiplying a vector by any positive real number except 1 changes the magnitude of the vector but not its direction. Multiplying a vector by any negative number reverses the direction of the vector. If k is a real number and v is a vector, the vector kv is called a scalar multiple of the vector v. And the magnitude and direction of kv are given as follows. Vector kv has a magnitude, the absolute value of k times the magnitude of v. All right, so you have to remember that absolute value of k, because k could be a negative number. The magnitude of a vector is never negative, right, because it represents a length. So we describe this again as the absolute value of k times the magnitude of v. Vector kv has a direction that is the same as the direction of v if k is positive, and the opposite, the direction of v if k is negative. All right, let's talk about the sum of two vectors. The sum of u and v, denoted u plus v, is called the resultant vector. A geometric method for adding two vectors is shown in the figure. So let me describe this to you. I'm not even going to look at the words over here. Here is vector u. So they've drawn vector v with its initial point corresponding with the terminal point of u. One thing that I haven't mentioned yet is that a lot of the time, see, a vector is completely determined by its magnitude and its direction. Its exact location doesn't really matter. So you can pick up vectors and move them around as long as you don't change their magnitude or their direction. So you pick up vector v, wherever it was, and you place it so that it starts at the terminal point of U, right? So I think of this as, you know, flying from one city to another city, and then I'm flying from that city to a place that I'm actually trying to go, all right, like a connecting flight. The resultant vector would be the direct flight, okay? From initial point of U to the terminal point of V. All right. The difference of two vectors, V minus U, is defined as V plus the opposite of U, where opposite U is the scalar multiplication of U and -1. So here's how the difference of two vectors works geometrically. So imagine starting out with these two vectors here. So the first thing I'm going to do is multiply U by -1 so that it changes direction. I'm keeping the terminal point where it was. Now I'm going to pick up this vector and I'm going to place it down over here, because what I really want to do is add the vectors V and opposite U. All right, and then remember how that worked when we talked about vector addition. The vector V plus opposite U will start at the initial point of V and will end at the terminal point of opposite U. All right, the I and J unit vectors. Vector I, let's see, have I told you what a unit vector is? I don't think I have. A unit vector is a vector whose magnitude is 1. So vector I is the unit vector whose direction is along the positive x-axis. So if you place it with its initial point at the origin, it would end at the point 1, 0. And vector J is the unit vector whose direction is along the positive y-axis. So if you place it at the origin, it would stop at the point 0, 1. So we can represent vectors in terms of I and J. The vector V from 0, 0 to AB can be represented as AI plus BJ. The real numbers A and B are called the scalar components of V. Notice that A is the horizontal component of V and B is the vertical component of V. So looking at this picture down here, starting at the origin, you go A units to the right and then B units up. And here is vector AI plus BJ. The vector sum AI plus BJ is called a linear combination of the vectors I and J. And the magnitude of V is given by this formula, which just comes from the Pythagorean theorem. All right, in this example, we'll sketch the vector V, which is 3i minus 3j, and we'll find its magnitude. So starting with the magnitude, using the formula that we just talked about. Okay, they actually could have just written square root of a squared plus b squared here. I think that would have been less confusing. All right, the square root of 3 squared plus the square of -3 comes out to the square root of 18, which simplifies to 3 square root of 2. And here's a picture of that vector starting at the origin and going 3 units to the right and 3 units down. So this is a vector that points 3 square root of 2 units directly southeast. Okay. All right, the vector V with initial point x1, y1 and terminal point x2, y2 is equal to the position vector whose scalar components are x2 minus x1 plus y2 minus y1. So that's something we use all the time. Like in this example, let V be the vector from initial point P1, which is -1, 3, to terminal point P2, which is 2, 7. We're going to write V in terms of I and J. So subtracting those coordinates, x2 minus x1 is 2 minus -1. Y2 minus y1 is 7 minus 3, which gives us 3i plus 4j. and there's a picture of that vector. So this kind of emphasizes the point I was making earlier, that it really doesn't matter where you put vectors. So it could go from -1, 3 to 2, 7, but if you pick it up and place it at the origin, it's the exact same vector. All right, adding and subtracting vectors in terms of I and j, you just add or subtract their scalar components. So if v is a1i plus b1j, and w is a2i plus b2j, then v plus w would be a1 plus a2i plus b1 plus b2j, and v minus w would be a1 minus a2i plus b1 minus b2j. All right, here's an example. If v is 7i plus 3j and w is 4i minus 5j, we're going to find the vectors v plus w and then v minus w. And, like I always say, whenever you want to try a problem first before I go over it, I totally encourage that. Just pause the video and then come back and compare notes. So to find v plus w, you would just add those scalar components. So you would get, for the I component, 7 plus 4. For the j component, 3 plus -5. You get the vector 11i minus 2j. And for v minus w, you just subtract the scalar components. 7 minus 4 for the I component, 3 minus -5 for the j component gives you 3i plus 8j. Scalar multiplication in terms of I and j. If v is ai plus bj and k is a real number, then the scalar multiplication of the vector v and the scalar k, you just multiply each scalar component by k. Okay, very simple. All right, so here's an example. If v equals 7i plus 10j, we want to find the vectors 8v and -5v. So just multiply, for letter A, you would multiply the components by 8. So that would give you 56i plus 80j. And for letter B, you just multiply the components by -5. And that would give you -35i minus 50j. The zero vector. The vector whose magnitude is 0 is called the zero vector, and is denoted by either a boldface 0 if you're doing print. If you're handwriting, then you should write that as a 0 with an arrow over it. All right, it is important to make the distinction between the number 0 and the vector 0. Okay, the zero vector is assigned no direction. I think of it as just a point. Okay. Zero vector, it can be expressed in terms of I and j like this. Its scalar components are both 0. Notice the boldface 0 here and the regular zeros over here. These zeros are just numbers. This 0 is a vector. Okay, it does take a little getting used to. All right, some properties of vector addition. If u, v, and w are vectors and c and d are scalars, then we have the following properties. First of all, vector addition is commutative. Vector addition is also associative. You have an identity element for vector addition, which is the 0 vector. Any vector plus the 0 vector, you just get back the same vector. And you also have additive inverses. Every vector has an additive inverse. That is a vector that when you add it to its inverse, you get the 0 vector. Okay. So you have properties of real numbers that are just like this, right? Real number addition. Real number addition is commutative, it's associative. You have an additive identity, which is the number 0. And you have additive inverses, which are just opposites, right? Like 5 and -5. All right, properties of scalar multiplication. Now, this is a little different from real number multiplication. First of all, you have this associative property. This is where they messed up with the boldface. C and D should not be bold-faced, but the U should be, okay? So when you, how do I describe this? When you multiply two scalars together and then multiply that by a vector, that is the same as multiplying the vector by one of the scalars first and then by the other scalar. Okay, that makes it associative. It is also distributive. This letter C should not be boldface. Basically, none of the letters C and D should be boldface in any of these properties. Here's another distributive property. The difference between this one and this one is that number 2 is talking about how to distribute scalars, and number 3 is talking about how to distribute a vector. Okay. That number 1 should not be boldface. This is just saying that the scalar multiplication of 1 and a vector is just that same vector. Okay, this one they actually got right. So the number 0 times any vector is the 0 vector. And then we talked about this one a little while ago, the magnitude of the vector CV, these C's should not be boldface, is the absolute value of C times the magnitude of V. All right, so now they're finally getting around to telling you that a unit vector is defined to be a vector whose magnitude is 1. All right, so this is really important. We're going to do this pretty frequently. This is finding the unit vector that has the same direction as a given non-zero vector V. For any non-zero vector V, the magnitude, the vector V over the magnitude of V. Now, technically, we didn't really talk about how to divide vectors by scalars. So what that means really is the scalar 1 divided by the magnitude of V. And because I'm handwriting this, I'm going to put an arrow there. That scalar times the vector V. That's technically what that means. We write it the way they printed it because we're lazy, which I admire. All right, that vector is the unit vector that has the same direction as V. So to find this vector, divide V by its magnitude. And now we understand what that means. Okay, so as an example, let's find the unit vector. And notice I keep stressing the unit vector. There is exactly one unit vector that has the same direction as a given vector. Okay. So we want to find the unit vector in the same direction as V equals 4i minus 3j, and then we'll verify that that vector has magnitude 1. So first we find the magnitude of V, which is given by this formula. The square root of 4 squared plus the square of -3 comes out to 5. So when we divide this vector by 5, we get 4/5 I minus 3/5 j. And now we're supposed to find the magnitude of that vector, verify that it's 1. The square root of 4/5 squared plus -3/5 squared is the square root of 16/25 plus 9/25, which does come out to 1. All right. Next, writing a vector in terms of its magnitude and direction. If V is a non-zero vector and theta is the direction angle measure from the positive x-axis to V, so just look at the picture, then the vector can be expressed in terms of its magnitude and direction angle like this. All right, so vector V is the magnitude of V times cosine theta I plus the magnitude of V times sine theta j. Okay, so I could convince you of that by drawing a triangle. All right, but I think I'll skip it. All right, you know I wouldn't lie to you. All right. And this is important because sometimes we have an example actually coming right up here. We're going to be given the magnitude and the direction of a vector, and we need to write its components. All right, just like in this example, if the jet stream is blowing at 60 miles per hour in the direction north 45 degrees east, remember your bearings, express its velocity as a vector v in terms of I and j. So using the formula that I just showed you, theta is 45 degrees. So notice that you have to convert the bearing to an angle in standard position. All right, this is a pretty simple example, but if it had said north 45 degrees west, then that direction angle would have been 135 degrees, right? And the magnitude of V is 60. Using this formula, we get that vector V is 60 times the cosine of 45 degrees, I, plus 60 times the sine of 45 degrees, J. And hopefully by now you know cosine 45 degrees and sine 45 degrees in your sleep. Those are both square root of 2 over 2. So the scalar components of this vector are both 30 square root of 2. The jet stream can be expressed in terms of I and J as 30 square root of 2 times I plus 30 square root of 2 times J. All right, this is my favorite kind of application problem for vectors. An example of resultant force. Excuse me. Two forces F1 and F2 of magnitude 30 and 60 pounds, respectively, act on an object. The direction of F1 is north 10 degrees east, and the direction of F2 is north 60 degrees east. Find the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree of the resultant force. And they've drawn you a picture of the two vectors and their resultant force. So here is F1 at a direction of north 10 degrees east, which means its direction angle is going to be, what is this angle right here? It would be 80 degrees, right? And here is F2 with a magnitude of 60 pounds and a bearing of north 60 degrees east, which makes its direction angle, what is this angle here? It would be 30 degrees, right? All right, so the first thing we're going to do is find the components of F1 and F2 using the formula that we just talked about. So the components of F1 would be 30 times the cosine of 80 degrees and 30 times the sine of 80 degrees, which come out to approximately 5.21 and 29.54. Similarly, the components of F2 would be 60 times the cosine of 30 degrees and 60 times the sine of 30 degrees, and that comes out to be about 51.96 I plus 30 J. Okay. So here's this picture again. Notice here is the resultant force. All right. And to completely convince you that that's the right picture, just imagine taking this vector, picking it up, and putting it down over here. We talked about how to geometrically add the vectors before, right? So this one is going all the way from the initial point of F2 to the terminal point of F1 once you pick up F1 and put it down over here. All right, so now that we have the components of F1 and F2, we're going to add F1 and F2 together, which is going to give us 57.17 I plus 59.54 J. And now that we have the components of the resultant vector, we can find its magnitude using this formula. The square root of 57.17 squared plus 59.54 squared comes out to be about 82.54. And then the cosine of theta, using some old hippies came around here tripping on acid, would be 57.17. Let's back up here for a second and show you why this is. So here is the angle theta. So if I drop a line from here all the way down to the x-axis, all right, the adjacent side to this angle would be the I component of the vector we just found. And then the hypotenuse would be the magnitude of the vector. Okay, just to explain where they got that, how they got this. All right, so the cosine of theta is equal to this ratio. And because we know this vector is in quadrant 1, we can just take the inverse cosine of that ratio, and we get that that angle is about 46.2 degrees. All right, so the two given forces are equivalent to a single force of approximately 82.54 pounds with a direction angle of approximately 46.2 degrees. All right, so that's our little introduction to vectors. You will hear more about vectors actually not until Calculus 3, but it's likely that you'll take a physics class before then, so hopefully this will be helpful. And that's what we got for section 6.6. So next time we will start looking at a few sections of chapter 9, and we'll see you then.